Hi everyone, welcome back for another lesson in stoichiometry. Today we're going to take a look at limiting reactants. Now in the problems that we've done up to this point, we've usually been told that there's an excess quantity of one of the reactants, and that essentially means that there's enough of that one reactant for the reaction to go to completion. But in reality, we don't just have an infinite amount of all the reactants, we usually deal with a fixed quantity of each. The limiting reactant is the reactant that will essentially run out first. Because we are often dealing with different starting quantities of reactants, and that they are often consumed at different rates, one reactant will usually run out before the other. Once one of the reactants comes to an end, the reaction is done, and you've reached the allotted amount of product that can be formed. The limiting reactant, the one that essentially runs out first in the reaction, is going to dictate how much product that can be made. The other reactant then is called the excess reactant, because there is still an extra amount of that remaining. Handling limiting reactant problems really isn't too much different from what we've been doing so far for stoichiometry. The only difference here is that we're giving two starting quantities rather than one. So this becomes a double stoichiometry problem. We do stoichiometry essentially two times in order to figure out how much product each reactant can make. The smaller quantity of product is the correct quantity that can actually be produced, because at that point you've run out of one of the reactants. So the limiting reactant is the one that makes you the smaller quantity of product, and that's how we can identify which reactant is going to determine how much product can be made. So let's take a look at a reaction and try to identify the limiting reactant. So in this reaction, we're told that aluminum is going to oxidize through the reaction between aluminum and oxygen. We want to first identify the limiting reactant if 1.17 moles of aluminum and 2.55 moles of oxygen react. Now you might see that we have a smaller quantity of aluminum than oxygen, and you might believe that because we've got a smaller quantity of aluminum, well, obviously that's going to run out first and determine how much product we can make. This is the wrong way to go about it, because even though, yes, the aluminum is a smaller quantity, the aluminum might actually be getting used up at a slower rate compared to the oxygen. So we really can't go based off starting quantities, and we should never go based off of starting quantities when it comes to limiting reactant problems. We have to go ahead and convert and try to identify how much product individually each reactant can make and then compare. So essentially we're going to do stoichiometry two times. My first set of stoichiometry is going to be taking the 1.17 moles of aluminum and determining how much product that can make. Since we're trying to find out how much aluminum oxide can be made, we're going to go ahead and convert our 1.17 moles of aluminum into aluminum oxide. And since we're already at moles, it's just a simple mole ratio, and it's a 4:2, or rather 2:4 ratio of aluminum oxide to aluminum. So if I have 1.17 moles of aluminum, I can produce 0.585 moles of aluminum oxide. Now we just repeat for the oxygen. So we're going to take our starting 2.55 moles of oxygen, and we're also going to convert that into aluminum oxide in order to determine how much aluminum oxide this quantity of oxygen can make. So if I start with 2.55 moles of oxygen, we can produce 1.7 moles of aluminum oxide. So what we did here is to kind of compare, if I have this quantity of one reactant, this is how much product I can make. If I have this quantity of the other reactant, this is how much product that can make me. So now we compare our two product quantities. The smaller quantity is the one that's possible. We call that the theoretical yield, because this is how much can actually be produced from the reaction. And the reason why I say it's the one that can actually be produced is because 1.17 moles of aluminum is how much we have. So once we've produced 0.585 moles of aluminum oxide, we have essentially run out of aluminum. So the reaction ends. This 1.7 moles of aluminum oxide actually isn't possible. Once we hit 0.585 moles of aluminum oxide, there is no more of one of the reactants, and so that's our limit for what we can produce. The 1.7 moles actually never forms. So the aluminum ends up being our limiting reactant, because this makes us the smaller quantity of product And once we hit that product quantity, the reaction comes to completion. Oxygen, because we made the larger quantity, is in excess, and so that's our excess reactant. So then the second part of our problem is how much aluminum oxide should you produce in grams? It was determined above that we can only make 0.585 moles of aluminum oxide. So essentially, this is the quantity that we're going to be working with. Since we can produce 0.585 moles of aluminum oxide, we just have to convert this into a mass, multiplying by the molar mass of aluminum oxide, to determine how many grams can be produced, which would be 59.6 grams of aluminum oxide. The limiting reactant is the one that determines exactly how much product can be made, and we call that amount of product the theoretical yield. Because based on these quantities, this is how much theoretically should be produced. And again, it's the limiting reactant that determines that. And all we got to do is just compare the amount of product that both reactants can produce, the smaller quantity being the true theoretical quantity that can be made. Let's see one more example of a limiting reactant problem, this time with a little bit more work required. So here's a reaction taking place in industry, and we're asked how many molecules of water can be produced from that reaction if 0.45 liters of ammonia and 4.2 grams of oxygen are available, assuming this reaction takes place at STP. So here we're given two starter quantities. We're told we have 0.45 liters of ammonia and 4.2 grams of oxygen. We're looking in the end for the total molecules of water. So we'll need to try to figure out exactly how much water is even possible to make based on the starting quantities. So when we're given the quantity for more than one reactant, that's essentially telling us we're dealing with a limiting reactant problem. So for a limiting reactant problem, we need to go ahead and figure out how much product each reactant can make individually and then compare. So we're essentially going to do stoichiometry 2 times. We'll do it once for the ammonia, the NH3, and then again for the oxygen. So we're going to start with our 0.45 liters of NH3, and we'll actually do this at the same exact time, having 4.2 grams of oxygen. Because we're trying to convert this into the same product, this time water, since we're asked for water, we're going to begin our stoichiometry. Well, in order to convert this into water, we need to have moles. And so our first thing is get our moles. So for the ammonia, we have liters. And to convert that into moles, we just need to divide by 22.4. For oxygen, since we're given a mass, we'll want to divide by the molar mass of oxygen gas. For ammonia, this means we have 0.02 moles available. And for oxygen, we would have 0.131 moles. Now again, we can't go based off the starting quantities. We have to convert this into moles of our product in order to really get an idea, because they can be consumed at different rates, and in this case, they are being consumed at different rates. So we'll have to convert these both into product, which in this case will be water. So for the ammonia, it is a 6:4 ratio, whereas for the oxygen, it's a 6:5 ratio. So that means 0.45 liters of ammonia can produce 0.03 moles of water. 4.2 grams of oxygen can produce 0.15 moles of water. So now that we have our two product quantities, the smaller one is our true moles. This 0.15 moles are not possible to form, because once 0.03 moles of water are formed, the reaction is essentially done, because we have run out of ammonia. So in this question, we're asked to find how many molecules of water can be made, and we've already determined that 0.03 moles of water can be made. So then it's just a matter of converting our moles into molecules by multiplying with Avogadro's number. So 0.45 liters of ammonia will be able to produce to us 1.81 times 10 to the 22nd molecules of water. Because the NH3 was our limiting reactant, that's the one that determined how much product we can make. So for limiting reactant problems, it's really just stoichiometry twice, one for each reactant, and the limiting reactant will produce the smaller quantity because once that's produced, the reaction's over. And it is the limiting reactant that determines the theoretical yield of the reaction.